This lesson deals with supplemental problem 317. You can find this problem in the course ebook in the Chapter 3 supplemental problem starting on page 23. What's shown below is what's called an instrumentation amplifier with a preamp. And you can see inside of it there's a differential amplifier. Now, differential amplifiers are often used to measure voltage across a floating load. In other words, things that are not grounded at either terminal. This is particularly true when trying to measure something like an EKG. I'm taking a difference of two voltages with sensors across someone's chest to pick up a heartbeat. Now, ideally, when you measure something, you don't want to change it. But remember, there is a current flowing in here and here that we had in our last supplemental problem. And these currents will change the value of V1 and V2 presented to the differential amplifier. The only way you can fix this up is to make those currents equal to zero. I'm going to add a circuit that's going to do just that. The current coming in here is the current of an op amp, and that's of course equal to zero. We'll show shortly that this actually creates a preamplification of the signal sensed out here, placed to this particular part of the circuit. Since we have a model for this differential amplifier in our last supplemental problem, let's replace this by its model. I'll make the analysis simpler because we already know what this is doing, and basically don't have to repeat those derivations again, and then we'll figure out what this is doing. This is shown on the next page. I'll call this node voltage V3 and this node voltage V4. My two inputs to the differential amplifier. The gain is going to be the difference of R4 and R3 times the resistor ratio, and I made the resistors the same ratio of R4 over R3. This was our model for that terminal, and this is the model for the other terminal. Of course, here's our rest of our op amp circuit, and let's label all the things that we know about this. Well, I have feedback around here, so the voltage across the op amps are driven to zero, and the current that's coming in here is zero and leaving is zero. Likewise for this op amp, what's entering and leaving, show it in either direction, still zero. The voltage V sub x here, I'm going to solve for shortly, is going to be this node voltage minus this node voltage. So minus 0 plus V1 back to ground, that's this term. This node voltage is going to be plus 0 plus V2, but I'm going to subtract that. The voltage V sub x is equal to V1 minus V2. I'm eventually going to solve for V out in terms of the difference of the two inputs. Let me go around this loop right here. The rising voltage is V3. The drop is going to be I2 R2, I2 times R1, I2 times R2 plus V4. Because the current coming from the op amp is zero, this current just circulates through here. I have an equation with, and the difference shows up here at the output, so let's set it up that way. I'll bring the on this side of the equation, so I have 4 minus 3, and I'm going to put the rest of this on the other side of the equation, but there's a common I2, and then I have R2 twice and R1. The other side of the equation becomes minus I2 times the quantity 2R2 plus 1. But I2 is the current in the resistor R1, and that's just going to be V sub x divided by R1. Then we showed that V sub x was V1 minus V2. We've got minus V sub x, V1 minus V2 divided by R1 times 2R2 plus R1. Let's bring the R1 inside here. Let's bring the minus sign on top here in the numerator. So I got V2 minus V1, get rid of that minus sign. And then I've got R1 divided by R1. And then I have 2R2 divided by R1. Now V out is just simply equal to R4 over R3 times V4 minus V3. So that's this expression here, but then V4 minus V3 is equal to this, which is 1 plus 2R2 over R1 times V2 minus V1. I've got the output in terms of the difference of the two inputs. If there's any noise common to those two voltages, they're just canceled. Pick up the differences. This again is very important when you're measuring something like a heartbeat, where there's noise on the common wires. Now because I have an op amp where V1 and V2 are connected, there's no current coming in, so my model for that is just an open circuit. And my output is just simply this voltage controlled voltage source, which is R4 over R3 times 1 plus 2R2 over R1 times V2 minus V1. The reason it's called a differential amplifier with a preamp is because of this expression right here. What's nice is that if I vary R1 with a pot, I can control the overall gain. This becomes a model for that instrumentation amplifier. This is supplemental problem 317.